Welcome. In this video, we'll be diving into the world of vector-valued functions, a powerful tool for describing motion in a plane. We're going to explore how these functions allow us to represent the position, and later, the velocity, of a moving object. By the end of this session, you will be able to do two main things. First, you'll be able to represent planar motion as a vector-valued function. And second, you'll be able to interpret the velocity of a particle from its vector-valued velocity function. We're going to build on your knowledge of parametric equations to understand this new way of describing movement over time. Let's get started. Our first objective is to represent planar motion using vector-valued functions. We can think of this as a new notation for something you might already be familiar with, parametric equations. Let's say the position of a particle at any given time t is described by a pair of parametric equations. One equation, x of t, tells you the x-coordinate at time t. The other, y of t, tells you the y-coordinate. Together, they form the position vector. We can represent this position as a vector starting from the origin. This is what we call a vector-valued function for position. We'll denote it with the bold letter r. It takes in the scalar time t and outputs a 2D vector. Notice the I and j components, which represent the unit vectors along the x and y axes. A key concept here is the magnitude of this position vector. The magnitude of r of t, which we write with double bars, gives you the distance from the particle to the origin at that specific time t. It's essentially the hypotenuse of a right triangle with legs x of t and y of t. So, to recap, a vector-valued position function gives us the location of a particle at any moment, and the magnitude of this function tells us how far it is from the center, 0, 0. Let's work through an example to solidify this. Suppose the position of a particle at time t is given by the vector-valued function r of t equals t squared plus 1, comma t cubed minus t. The question is, what is the particle's distance from the origin at time t equals 2? First, let's find the position of the particle at t equals 2. We do this by plugging 2 into our function. The x component is 2 squared plus 1, which is 5. The y component is 2 cubed minus 2, which is 8 minus 2, or 6. So the position is the vector less than 5. Now, we can visualize this on a graph. Here's our xy plane. The position vector is drawn as an arrow starting at the origin and ending at the point 5, 6. To find the distance from the origin, we need the magnitude of this position vector. Remember the formula. The magnitude is the square root of the sum of the squares of the components. So we have the square root of 5 squared plus 6 squared. That's the square root of 25 plus 36, which equals the square root of 61. So, at time t equals sign 2, the particle is a distance of square root of 61 units from the origin. We have now used a vector-valued function to find the position of a particle and calculated its distance from the origin by finding the magnitude of that position vector. Now let's move on to our second main objective, interpreting velocity from a vector-valued function. Just as the position vector tells us where a particle is, the velocity vector tells us how fast it's moving and in what direction. We can get the velocity vector, denoted as v of t, by taking the derivative of our position vector r of t. How do you take the derivative of a vector-valued function? It's straightforward. You just take the derivative of each component separately. So, the x component of the velocity vector is the derivative of the x component of the position vector, x prime of t. Similarly, the y component is y prime of t. Now, let's understand what these components tell us. The sign of the x component of velocity, x prime of t, indicates horizontal motion. If it's positive, the particle is moving to the right. If it's negative, it's moving to the left. Similarly, the sign of the y component, y prime of t, indicates vertical motion. A positive value means the particle is moving up, and a negative value means it's moving down. The magnitude of the velocity vector gives us the speed of the particle. This is a very important concept. The magnitude of the velocity is equal to the square root of x prime of t squared plus y prime of t squared. This is our speed. To be clear, velocity is a vector that tells us direction and magnitude, while speed is a scalar that only tells us the magnitude of that velocity. So, the magnitude of the velocity vector is the speed. Let's continue with our previous example and find the velocity and speed. Our position function was r of t equals the vector less than t squared plus 1, t cubed minus t greater than. First, let's find the velocity function, v of t. We take the derivative of each component. The derivative of t squared plus 1 is 2t. The derivative of t cubed minus t is 3t squared minus 1. So our velocity vector is less than 2t, 3t squared minus 1, greater than. Now, let's find the speed function. The speed is the magnitude of the velocity vector. That's the square root of the square of the first component, 2t, plus the square of the second component, 3t squared minus 1. Expanding that out gives us the square root of 4t squared plus 9t to the fourth minus 6t squared plus 1. Simplifying, we get the square root of 9t to the fourth minus 2t squared plus 1. This is our general expression for the speed at any time t. Let's find the specific velocity and speed at t equals 2, just like we did for position. Plugging t equals 2 into our velocity function, we get 2 times 2 for the x component, which is 4. For the y component, we have 3 times 2 squared minus 1, which is 11. So the velocity at t equals 2 is the vector less than 4, 11 greater than. This vector tells us the particle is moving to the right because the x component 4 is positive, and upwards because the y component 11 is positive. For the speed, we plug t equals 2 into our speed formula. This gives us the square root of 137. At time t equals 2, the particle's speed is square root of 137 units per unit time. We've now found the velocity vector, interpreted its components for direction, and calculated the speed. Let's explore another example to see a particle that changes its direction. Consider the position function r of t equals the vector t squared minus 2t, t cubed minus 3t. Let's find its speed and direction at t equals 1 and t equals 2. First, we find the velocity vector by taking the derivatives of the components. The derivative of t squared minus 2t is 2t minus 2. The derivative of t cubed minus 3t is 3t squared minus 3. So, v of t is the vector 2t minus 2, 3t squared minus 3. Now let's analyze the velocity at t equals 1. Plugging in t equals 1, we get v of 1 equals the 0 vector. When the velocity vector is the 0 vector, we say the particle is momentarily at rest. Its speed, which is the magnitude of the 0 vector, is 0. This means it has stopped moving at t equals 1. Next, let's look at t equals 2. Plugging in t equals 2, the velocity vector is v of 2 equals the vector 2, 9. The speed is the magnitude of this vector, which is the square root of 2 squared plus 9 squared, or the square root of 85. Since both components of velocity at t equals 2 are positive, this tells us the particle is moving to the right and upwards at this moment. Notice how the particle's direction of motion and speed changed after passing through the rest point at t equals 1. Let's work through one more example where we might need to use a calculator. Suppose a particle's position is given by r of t equals the vector t cubed, the sine of t squared. We want to find its speed and direction at t equals 1.5. As always, we start by finding the velocity vector. The derivative of t cubed is 3t squared. The derivative of sine of t squared requires the chain rule. It's cosine of t squared times the derivative of t squared, which is 2t. So, v of t equals the vector 3t squared, 2t cosine of t squared. Now we plug in t equals 1.5. For the x component, we have 3 times 1.5 squared, which is 3 times 2.25, giving us 6.75. For the y component, we need to be careful with our calculator. First, make sure your calculator is in radians mode. Then, calculate 3 times the cosine of 2.25. This gives us approximately negative 2.05, so the velocity vector is approximately 6.75, negative 2.05. From this vector, we can interpret the particle's direction. Since the x component is positive, 6.75, it's moving to the right. Since the y component is negative, negative 2.05, it's moving down. So at t equals 1.5, the particle is moving down and to the right. Now let's find the speed at t equals 1.5. The speed is the magnitude of the velocity vector. That's the square root of 6.75 squared plus negative 2.05 squared. This calculation gives us approximately 7.05. So, at this moment, the particle is moving at a speed of about 7.05 units per time. In this scene, we saw how to work with trigonometric functions in vector-valued functions and used a calculator to find and interpret the velocity and speed at a specific time. Let's quickly recap what we've covered today. We started by representing the motion of a particle in a plane using a vector-valued position function, r of t. We learned that its magnitude gives the distance from the origin. Then, we introduced the velocity vector, v of t, which we get by taking the derivative of the position function. Its components tell us about the direction of motion, left/right, and up-down. Finally, we defined speed as the magnitude of the velocity vector. This is a crucial distinction. Velocity is a vector, while speed is the scalar magnitude of that vector. You are now equipped to represent planar motion with vector functions and interpret the resulting velocity and speed. These concepts form the foundation for many more advanced applications in physics and engineering, so a solid understanding is incredibly valuable. Thank you for watching.